This is AP2 review day 1 for our semester final at the end of the year, which will cover everything on the AP test. So this particular talk, speech, lecture review is on a couple different, lots of different topics, fluids, thermo, electrostatics, and E-fields. So it's kind of a combination of a whole bunch of stuff. So let's start with fluids. So with fluids, our basic equation is that the total fluid pressure is P equals P naught plus rho GH. So the concept with this one, right, is that if I've got something here and then I've got like maybe this is a liquid and then I have an object that's sitting right here and then maybe I have air or something up here, you can just keep adding up the pressure. So the only thing I care about is the height. Oh, you can't read that. The only thing I care about is the height above it, right? And it's additive, so I can add rho GH plus rho GH, and then you always add atmospheric pressure at the top. So maybe this isn't air, maybe it's some other gas, I don't know. Anyways, it's additive, so all we care is how much is going up. We don't care, volume is unimportant, right? So we don't care about volume. Pressure equals force per area. Remember that the pressure only acts in one direction, so we don't care about anything else like that. So again, we're looking at just the height above it. That's what's important about it. And it's force per area that's perpendicular to it. So if I've got a round object like that, I know I drew it with a line, but if I have a round object like that, then I only care about the force that is perpendicular to the surface causing the pressure. Rho equals m over v is our density, and remember our rho here can replace our inertia, our mass, in a lot of our kinematics equations. So like kinetic energy becomes, here we have it, 1/2 rho v squared, mgh becomes rho gh, because we just care about the density of it. Buoyant force is rho vg. Remember that this is the volume of fluid displaced, it says fluid displaced, not the volume of the object, unless the volume is completely submerged, right? If I have water and I have an object on top, then this is the volume, right? That's the volume I care about. But if the thing is totally submerged, then the volume is the entire volume because it's totally submerged. But the rho, right? This rho is the rho of the fluid, right? Not of the object, because that's what's causing the buoyant force. That's the concept. Continuity equation just says A times V has to equal A times V. We just have conservation of mass because you have so much stuff going in. That means if A goes down, V goes up, because A is proportional to R squared. Basically, you have R squared, like if that was 2 over R1 squared, is going to be the inverse ratio. Oops, that is not the inverse ratio. It's going to be the inverse ratio of the velocities, right? So if R2 goes up, V2 goes down, right? Because it has to stay the same. And the Bernoulli's equation is just the concept that it stays constant. This is all energy, right? So P is like my work, and rho GH is my my potential energy, and 1/2 rho V squared is my kinetic energy, how fast it's moving. So if you look at all the energy, it has to stay constant because of conservation of energy. So just a couple things to remember. Pascal is the pressure. For Pascal, the pressure is the same in all directions. So if I have an enclosed system, right, this is like having a hydraulic lift or something. If I have pressure over here, the pressure has to be same over here. So if you change the area, you get more force, you can get more lift out of it. This has to be enclosed, right? If you have openings, that's not true, because then the pressure can basically escape right out into the atmosphere, and then you don't have the pressure, moving through the whole system. Archimedes, remember we said that already in the last slide, that FB is the weight of the fluid displaced, not the object. So the harder you push down, the more fluid you displace, the bigger the buoyant force. It can be equal to the weight, but doesn't have to be. Depends on if it floats or sinks. If it floats, then it's equal to the weight of the object. If it doesn't, then it's just equal to rho Vg of the liquid displaced. Continuity, we said that already. There's an inverse relationship. As A increases, V decreases. And Bernoulli, we already said that Bernoulli's conservation of energy, and it's just the pressure, the kinetic energy, the potential energy stays constant. Pressure is like work, so we kind of said that. Reminders, fluids are both liquids and gases. We don't care which one that is. Just a useful fact is about every 10 meters of water, there's about 1 atmosphere, since rho Vg, right, or it's rho Gh, and rho is 1,000, and then times 10, and then 1 meter, so that's about 1 times 10 to the fifth, because remember, atmospheric pressure, right, P atmosphere is equal to 1 times 10 to the fifth pascals. That is given on your table of information, so you don't have to memorize it. If you want to convert density in grams per centimeter cubed to kilograms per meter cubed, you just simply multiply by 1,000, since the density of pure water is simply 1,000. I don't think they give that to you, but that's something you should just know, that it's 1,000 kilograms per meter cubed. An object that floats has a buoyant force on it equal to its weight, right? So the key here is that it floats, right? If it floats, it's equal to its weight, but if it doesn't float, it doesn't. If it sinks, right? If it sinks, then it's less than its weight. Continuity equation is conservation of mass, because you have the same amount of stuff that has to go through per second, and Bernoulli is energy, right? So it's just concepts to think about as you do the AP test. Then we get on to thermodynamics. So here are the basic equations. There's a few more that are listed in here, but these are the main ones. So if work is equal to negative P delta V, remember that negative is important in a sense, because if volume increases, then you have negative work done, because it is doing work on the surroundings. Remember, we talked about the difference between the surroundings and the system. And so these equations are for on the system, not the surroundings. So remember that these equations here are for the system. And so if it's, so this would be by the system, or it's for the system, right? So it's going to lose energy if it gets bigger, right? That's the concept. Delta U would be positive if it gains it. So it's this, what's going on with the system is the best way to look at it. If you do work on the system, you increase. So I guess you could say it's on the system. I'm worried that that's not specific enough, or it's not always, but I try to think of a case when it's not. But if you understand the concept, right, that the volume increases, it's losing energy. That's why the work is negative, right? If you do work on it, so this is positive, it makes sense that you should increase in internal energy, right? It's getting more stuff. If I add heat to it, it should have more internal energy. So just make sure the concept makes sense. Efficiency is basically how much you get out for how much you put in. So remember, QH is the hot reservoir. I can't spell reservoir. Can I do it like that? And then you guys can spell it right. It's the hot reservoir. So that's basically the input energy, and then work is basically the output. And then QC is the wasted, right? The wasted energy, because I can't do anything. It's what makes the whole thing go. If this one here is only for Carnot, right, which is the most efficient system. Remember, for our Carnot engine, it kind of does this kind of thing. It's like all concave, and it goes adiabatic, isothermal, adiabatic, isothermal. I don't think they're going to get that specific on it. They'll say the most efficient, right? Most efficient Carnot, right? All those things mean the same thing. These are chemistry equations, just nice to know. Delta Q equals MC delta T. You can do that for a gas, but then you have to use CP if it's under constant pressure, and N for the number of moles, right? So it becomes delta Q equals N, for example, CP delta T. That would be under constant pressure, and delta Q V equals NCV delta T if it's at constant volume. But they'll always make it so you don't have to do that, but it's just something to kind of remember. If you do use this equation, PV equals nRT, you have to be careful because if P and V are changing, then it doesn't work. So P and V have to be constant. Or you could do like P delta V equals NR delta T, and then that would work because you have two deltas. But if you have delta P, then you have a mess because you don't know what's going to happen if P and V are both changing, and you can't set it to equal to N. Well, I mean, it is equal to it, but it doesn't make it useful because P and V can change in so many different ways to make that equality. It's really not useful. Anyways, so those are our main. And whoa, didn't mean to do this. So remember when we're looking at heat energy transferred, is the energy transferred? So heat, you don't contain heat. Heat is what moves due to a temperature difference. And so our kinetic energy, remember, is equal to 3/2 kT, which is equal to 1/2 mv squared. So that becomes useful. A lot of times you can set those equal if you want to use those. Remember this M, one of the things to point out, this M is of one molecule, right? So you have to make sure you have the right information to use that one. And this K, remember, is KB, which is Boltzmann's constant. I don't remember off the top of my head, but it's on your table of information. I think it's 1 point something something times 10 to the negative something. Anyways, it's there. It's on your table of information. Nothing you need to memorize. Just know that that's KB, right? Boltzmann's constant. You do need to understand these words, isothermal, adiabatic, and isochoric. Isothermal means that the temperature stays the same, so that's why this one says delta T equals 0. If delta T equals 0, remember delta U has to equal 0. So that's one of the things we like is because delta U is equal to, let's try again. U is equal to 3/2 nRT. If T changes, U changes. If T stays constant, U stays constant. That's the only constant thing we have. Everything else is depends on other things. But temperature and internal energy are the same thing. Not heat, not heat. I don't know how much I can say that. So U is not the same as heat because heat is Q. Right? And Q can change all different things. You don't have to change temperature. You can simply change state if you add or take away Q. So remember that heat and U are not the same thing, and so it's not the same as temperature. Heat, that is. Heat is not the same as temperature. U is the same as temperature, right? Those two things are equivalent statements. So the result of the first law is, delta U equals Q plus W, so you end up with Q equals negative W. Because it's isothermal, we really can't say anything else about that. If it's adiabatic, it's delta Q is equal to 0, and delta U is equal to W because now you have no Q in it. That just means there's no heat exchange. And if delta V is equal to 0, then work is equal to 0, and delta U is equal to Q. I notice there's no isobaric, which is kind of interesting. So let's put that in there. So isobaric means that delta P is equal to 0. So now you can do P delta V is equal to NR delta T because your P is staying constant, right? Because this would be one that looks like PV. It'd be like this, right? Because it's at a constant pressure. So you could use that equation in that case. And I believe this one comes out to be 5/2 nRT if you look at the delta Q, right? Because delta Q would therefore be equal to work plus P delta V because of the negative in there. And since this is nRT and, that's not, hang on. This is not W. This is Q. No, this is P delta V delta U equals delta Q plus W. And so that means, be delta U. I knew that. You knew that. And so delta U is 3/2, right? It's 3/2 nRT. So then you have the 3/2, right? So if you have 3/2 plus 2/2, that's where you get the 5/2 nR delta T for your delta Q now, right? So those are the kind of concepts you have to kind of play around with in your mind as you are doing them. Yeah? PV graphs, the area, right? And the area in this case is the area. I drew this one in already, so I left it. So you can add it to yours. But if we do a PV then the area is the work done. You have to figure out if it's positive or if it's negative based on which way it's going. In this case, since it's bigger, going in that direction, so that's a positive V, so that would be negative work because it expanded more than it contracted. And you just simply, if it's a triangle, you can just find the area, and that makes life really nice. Again, if you increase V, it's negative. If you decrease V, it's positive. If there's no change, so right there where there's no change, then my work is equal to 0. And of course, delta U is always equal to Q plus W if you're doing your math. Thing to mention on this, sometimes I find it really useful to just find your PV, P, V, and T at each point. I just find that useful, so then you can start deciding if the temperature is going up or the temperature is going down to help you figure out what signs these are, right? Because you know that PV over T is always equal to PV over T. So if you know one of them, you can figure out the other one, right? So lots of the times they'll say, we'll start at this temperature, and then you can just figure out the PV over T for each one. It just, for me, makes it easier when I'm doing the problems. I have trouble conceptually. Oh, one was figuring out if temperature went up or temperature went down. Heat engines, efficiency and entropy. So heat engines take in heat as QH, and then they do work, and they give off wasted energy. We talked about that already. In the process, QH equals W plus C, so QC. So this one we didn't have on that first page, but that's a good one to remember as you're trying to calculate things. All right, we already said that the efficiency was work over QH, and the most efficient was 1 minus TC over TH. We didn't mention anything about entropy, but it's delta S over T. You do need to pay attention if it's negative delta S or positive delta S, right? So if I'm going towards a gas, I'm increasing my entropy, so that would be a positive delta S. But if I'm going from a gas to a solid, then it would be negative delta S, right? So if I go solid to gas, right, more entropy, so delta S would be positive. And if I go gas to solid, then that would be a negative delta S. And there's no way to really figure that out unless you know what it's doing. And then remember that that T better be in Kelvin. The only T's you can do in Celsius is if it's a delta T. Delta T's can be in Celsius. Otherwise, if it's a T, remember, it has to be in Kelvin or it doesn't work. Reminders, there it is. All temperatures need to be Kelvin in ideal gas equations. For the AP exam, work done on the system is positive. You decrease the volume. We've said that many times. Work done by a system is negative. It's just because it's defined so many different ways. But on the AP exam, I guarantee that's how they're going to define it. And on a PV diagram, the net work done for any process. And remember, that is the net work done by any process described by a set of steps in a closed loop is the area, right? If that's just the network, if you're trying to figure that out, which sometimes is important. For electrostatics in E-fields, last section we're going to talk about. Here are some of the equations. So you should know Q over R squared. Notice that K is 9 times 10 to the 9th. But technically it's 1 over 4 pi epsilon naught. They give you epsilon naught. I believe they even give you this. I think this whole thing, I'm 99% sure that's on your table of information. So no memorization needed. You just know it's there. We know it's an inverse square law. We know that E fields are inverse square law because remember, we know that E is F over Q. So you notice one of the Q's is gone, right, as we're doing it. But it's all over R squared. So these are both inverse square laws. This Q right here is the Q that's in the middle, right? So charge is always conserved. So if you're looking at how things are charged, you can make sure that the total charge has to stay the same. So if you have two things that add up to positive 5 coulombs, at the end of them doing whatever they do, unless there's somewhere that's taken away, they have to end up with positive 5 coulombs. You should understand the concept of polarization. Polarization is when you separate the charges, right? So if I take we've done this before, you take my negative balloon, and then we have positive charges over here and negative charges over there. That's called polarization. So now they attract because these two things are polarized. They will not stay polarized if you move this away unless you ground it. So if I ground this and I send some of those extra electrons, I can make that become positive, but otherwise it stays neutral. So it depends on if you ground it or not. And so you always attract, though, if you bring the opposite charge, if you bring any charge, right? Because if it's a positive balloon, then the negatives would come over here, and so it would still be attraction no matter what. Forces, electric forces are vectors. You have to add them as vectors. That's why they're a pain in the neck. They're not difficult, but you do have to calculate them as vectors. So if I have a positive charge here and it has a force going this way and it has a force going this way, then I have to add them up and figure out the net force here. It's just a pain, but it's not hard. Just remember how to find your components and all that and add them up. 90% of them are going to be 90 degrees. You can use Pythagorean theorem. They're not going to do a lot of cosine sine stuff because they don't want to waste the time for that. E-field, same thing. They are vectors, and they're defined, remember, by a positive point charge. That's super important. So if I have a positive charge right here and I want to know the E-field in this case is pointing in that direction because that's the way a positive charge would go. On the other hand, if I had a negative charge, then the E-field would be pointing this way, and that's the only thing different, but the magnitude would be the same, right, because it's defined by positive test charge. That Q, right, if we go back to Q, is this Q right here, right? That's defining that E-field at some point in space, right? But it's just what the electric field is. So if I put something there, I can figure out what the force is, or I can figure out what the electric potential is. So drawing of E-forces, I kind of did that a little bit. So if I have a positive charge here and it's got a negative charge here and a positive charge here, we call this one number 1 and this one number 2, then I know that number 1 is going to have a force on it pushing it this way, so that'd be F1. This one would be F2, and then I know the total force would be the square root of F2 squared plus F1 squared, right? If I wanted a drawing of a point E-field, so here is my positive charge. E-field would go like this. If it's a point charge, it's non-uniform. It decreases as we go further out, right, because the lines are further apart, follows inverse square law. If it was 2-point charges, right, so if we had a positive and a positive, for example, then it would have a 0 in between because a positive charge would go like this. If it was negative and, I said negative, I wrote positive. If it was a negative and a positive, then the E-field would go from positive to negative like this, and then this one would be all pointing in, and this one would all be pointing out. If it's a uniform, and the only thing different if this was negative, it would point, right? If this was a negative and a negative, then it would be the same thing, but pointing in the other direction, right? Pointing in. And then the drawing of a uniform E-field, so if I have a positive up here and a negative down here, then I know my E-field points positive to negative, and it's uniform, so the spacing, you notice, is all the same. And so this equation, right, so E is equal to, oh, sorry, that's not the way I remember it because I do it backwards. It does give you the equation, but I always mess it up. So I always say delta V equals E D, where D is the distance here and delta V is the difference in V, right, between those 2 points. Remember we talked about if it's uniform, you know that V is stepping down the same amount. It's proportional to D. Right, but E stays the same, so you end up with E is equal to delta V over delta D, because that stays the same. Yeah? Oh my God, that's a mess. Reminders, electric force and electric fields are vectors, so you have to the vector components must be used to add with addition to separate and direction. Watch for symmetry when working with electric fields. Situation when the components cancel. So lots of times they might put it on a, like they're looking at the one at the origin, and maybe that's positive, and then there's a negative guy up here, and maybe a negative guy, my goodness, it's a negative one over here, right? And so I'm trying to think if that's the way they work. Maybe we're going to look at the force on this guy. Oops. We're going to look at the force on this guy right here. So I'm trying to figure out would that work. So this one would point negative to positive like that. And then this one up here would go down. I guess there's nothing that really cancels on that one. But they will sometimes have it. So if you look at it, there's some symmetry. You might have some canceling on it. That one doesn't. Sorry. Magnitudes of electric forces and electric fields follow the inverse square law. We said that a couple times. Oh, this one's important to remember, that no electric field exists inside a conductor. So if I was looking inside a conductor, that the E field inside here is always going to be 0, as long as this is a metal. That has to be a conductor, right? If it's not a conductor, it doesn't work. And excess charge placed in the conductor will move to the conductor's exterior. So the positives would all be like out here, or the negatives or whatever, and then the E fields all cancel in the center. Last thing I want to remind you is that if you find the E field someplace, then you don't need to find the force again when you put a point charge there. So let's say I had some charges, right? And this was positive, and this was my negative one, and this was my positive one. I don't know. I don't think they're making anything that difficult. Actually, let's take that one out. But let's say I wanted to know the E field right here, right? So then I would say, okay, so my E field positive, if I put a positive right there, it's going to go that way. So that would be E1 if this is number 1. And this one, let's say that's negative, so it would pull it in like this. So this is E2. So I add them together, right? I add my component this, and I add my component there, right? So I subtract this one from that one. I do Pythagorean theorem, blah, blah, blah. And let's say my E total comes out to be, I don't know, let's just make it 10 newtons per coulomb. Then I know that if I bring a charge there, right, and I know what the charge is, I can simply take E times Q to figure out the force. I don't have to do KQQ over R squared again, right? But you have to pay attention to the direction, because a positive, right, a positive goes with the E field and a negative goes opposite the E field, right? So little tips as you're doing it. That's it.